Yeah, thanks. I'm continuing on for the theme for the day, which is delta matroids of various sorts. So Matt told us at the end of the last talk that we could make two different choices when dealing with delta matroids, and I'm for the most part going to make the opposite choice from the last talk. So we'll see what happens. So this is joint work with Nathan Cheung, Tracy Chin, and Gaku Liu, all of whom are at UW with me. So I want to talk about one possible notion of valuated delta matroids and realizations thereof. I was originally going to review all of the known stuff about the usual valuated matroid and even valuated even delta matroid story. I might still do this, but I might go quicker given that we've seen a lot of it today. But just so as a reminder, so valuated, we'll start with the story that probably many people are familiar with, is valuated matroids, which one can think of as functions. If our ground set is the numbers 1 through n, and we're interested in matroids of rank R, we can think of these as functions from R union to infinity, satisfying an inequality version of the basics exchange axiom, namely that if I pick any two subsets and I pick an element, say I, that's in one but not the other, then I can find another element, J, say in T, but not S, such that some inequality holds. The value at S plus the value at T should be greater than equal to S, where we flip, so we add in J, we get rid of I, plus the value T, where we add in I, get rid of. In particular, this will imply that the support of this function, namely the subsets at which it takes finite value, are the bases of a matrix. And there's lots of equivalent ways of writing down this condition, the equivalent conditions. One, I think was proved by Dress and Wenzel, was that one, if you know already that the support, which is again a set of subsets for which this function does not take value infinity, if you know that this is a matroid, then these inequalities, to check all of these inequalities, it's enough to know that the values of this function satisfy what's called the three-term Fluker relations. What's the three-term graphical Fluker relations? The minimum of three things is attained at least twice. And another is that if we look at the regular subdivision, so this is some function on subsets of size large, numbers 1 through n, which we can identify with their indicator vectors. We can think of then these functions as heights, and we get a regular subdivision induced by taking the lower hull. The equivalent condition is that all edges of this subdivision are in the correct direction. So all edges of the regular subdivision are induced. Like this on the convex hull of its support are on convex hull of really the indicator vectors of support. Are parallel to EI minus EJ. That means that all cells in this subdivision are Matroid polytopes. Okay. And the set of all evaluated Matroids on and choose R, known as the Dressian. The R and Dressian. And we think of one of these creatures as being representable if it really comes as the valuations of minors of some R by N matrix. So representation is we have some matrix or a field with evaluation or rank R. And then we take the function value at S, which is going to be the evaluation of the minor, where we pick out the columns indexed by. This is a very small example. We take a 2x4 matrix. Maybe we work over the Bestow series. We can check that the evaluation of all of the minors except for the last one is 0. Not equal to 4. And if you take the 2x2 minor, the 3/4, 2x2 minor, you're going to have just a T, which has valuation 1. And indeed, if you look at this is the one sort of Matroid polytope we draw. We look at the indicator vectors here. The underlying Matroid is the uniform Matroid. The polytope is the convex holocal 0, 1 vectors with exactly 2 ones. In this case, the regular subdivision, what happens is all vertices except for 1 are stuck at height 0. We pull up the vertex with 1s and 3/4 to height 1. And then in the lower, so this is height 1, 0. And then we get the Matroid sub, everyone's favorite matroidal subdivision, where we break the octahedron into 2 square units. That is indeed a subdivision into Matroid polytope. So far, there's nothing so new. Yeah. So I want to talk about, I mean, we've seen again some of this already. Today I want to talk about extending this to delta matroids. So we've seen various definitions. I want to take delta matroids where I'm really thinking of non-empty, so my bases or admissible sets as a collection of subsets of 1 through n. That should be non-empty. And satisfy the exchange axiom that if I have 2 and I have an element that's in their symmetric difference, then there exists another element in their symmetric difference. Such that the symmetric difference of S ij is again what we'll call a basis. And as with many other things, so equivalently, I think this was in the book. Baxter matroids, all edges of the polytope. Solve S and C are parallel to now EI or EI plus or minus EJ. So for example, the sort of things that we're now allowing into our lives is we could take, say, the empty set, all even subsets of 1, 2, 3, and then 1, 2, 3 itself. This is, we could draw the corresponding polytope as a subset of the 3 cube. We pick the empty sets corresponding to 0, 0, 0. We pick all of the vectors with 2 1s, and then we pick the vector 1, 1, 1. And check that the convex hull only has edges. Here we have an edge parallel to EI plus EJ. Here we have an edge parallel to EI minus EJ. Here we have edge parallel to EI. Just to match up with the other definitions we've seen today here. So here, from the multi-matroid talk that we saw yesterday, you can think of this as multi-matroids with 2 colors. And equivalently from the transversal, from all the other talks we saw today, from any subset, you can think of associating to it. So if you have some subset of 1 through n, if you want to view this as like transversals, like we saw this morning, of n and then another copy of the numbers 1 through n, then to any subset S, you can associate like S union the barred star, or her bars or stars, a starred version of its column. Inside of like n union and bar is a copy of 1 through n that are colored with bars. Okay. And so an example from one of the early papers on this, Boucher, is that if you have a matrix, an n by n matrix, that's either symmetric or skew symmetric. And you record which of its principal minors are non-zero. So for every subset of 1 through n, you can look at the matrix A and pick out the rows indexed by S, the columns also indexed by S. Take the determinant of the principal submatrix you get this way, which I'm going to denote as AS, and just collect the subsets for which this is non-zero. And this will be a delta matrix. So easy examples, we pick A to be a skew symmetric matrix. Then we get and we always have the empty minor as being 1. So the empty minor is always non-zero. A empty set, we're just going to count as 1. In particular, it's always going to be a basis coming from such a thing. For this, the diagonal entries are 0, so the singleton sets, the singleton principal minors do not show up, and then the determinant is non. If we picked the symmetric matrix, then again, we always have the empty set. We don't have the singleton minors. In fact, all the 2 by 2 minors are non-zero. And also that the determinant of this matrix is non-zero. So we're not working over a characteristic. Okay, which is exactly this delta matroid that we cooked up there. it's reasonable to ask, like, which ones are representable in such a way? And is there a evaluated version of this story? We've already seen that some of the answers are yes. And the warning, which we saw in the talk just before lunch, is that the strong exchange axiom does not hold in general matrix, right? So this exchange axiom okay. Does not in general imply the strong exchange axiom, which would be the same plus the conclusion that also the symmetric difference of T in these elements is also a basis. We saw a failure of this in the morning talk. It also fails for this matroid in blue. So in the example above, if you take S to be the empty set and T to be 1, 2, 3, and I to be anything, it's symmetric. If you say 1, then it's still true. This is still a delta matroid. It's still true that you can find a J. J is going to be 2 or 3, such that symmetric difference of S and IJ is a basis. You can, so for star, and pick J equals 2 or 3. But then it's immediate that if this is a subset, really, these numbers are going to have to be distinct. The symmetric difference of T with this subset of size 2 is going to be a subset of size 1, which is not going to be based. So we really don't have the strong exchange axiom, which is what people usually use to define, like here, to define valuations, to define what the notion of like a valuated matrix. And so in this talk, rather than extend our notion of what we want from so rather than add in more sets, we're just going to plow through and say, okay, we accept we don't have, we accept that we don't have the strong exchange axiom, and let's see what happens. So maybe I'll point out, in the case of even delta matroids, as I mentioned before, things are still quite nice. So even delta matroids. So this is one way of writing this down, is if you in particular require that I and J are distinct in this exchange axiom. Or equivalently, if the edges your polytope are parallel to just EI plus or minus EJ, you're not allowed to go in a single coordinate direction. And for these nicely, you do still have a strong exchange axiom, and so there is a natural notion of a evaluated even delta matroid. Evaluated delta matroid. And here, so this will be a function on subsets of 1 through n, R union infinity. Satisfying that from 2 subsets. So it looks like an inequality version of the strong exchange axiom. And my symmetric difference, this is a difference such that the value of S plus the value of T is greater than or equal to the value of symmetric difference of S with ij, plus values, the symmetric difference.
Just in your example, if you switch around as on T, why doesn't it break?
Good. So if you're allowed to take I equal to J, I mean, that's the reason. Is so if S is, no, if T is the empty set and S is 1, 2, 3, and I pick I equal to 1. Hopefully this works. I think between all of us, we can do this. So then I'm allowed to pick a J in the symmetric difference, and I'm allowed to pick J equal to I. So then I just have to produce J. I'm going to pick J also equal to 1. That's allowed. And then the symmetric difference of S with just the set 1 is 2, 3. Which is a basis. Yeah. And that's explicitly what we're sort of not allowing when we do even delta. Yeah.
So when you write star plus the symmetric difference, does that mean that you're picking the same J?
Yeah. So I mean, in the conclusion is that both S symmetric difference, these two, and T symmetric difference, the same two is a basis.
There is one J.
Yeah. For even delta matroids, it's the same. You can check that this actually sort of implies that version. So if you think about how inequalities in infinity work, it will imply that, but if both of these are finite, then both of these have to be finite. Yeah, good. Okay, and so these were studied by other people, so Felipe, 2010, and in particular he showed that this condition is equivalent to sort of analogous things for the matroid. Condition 1 is that the support is a delta matroid, and that it satisfies the so-called 4-term weight relations.
Even delta matroid.
Even, thank you. Even delta matroid. Which are relations that hold on the Fathians of skew symmetric matrices. And equivalently, at all edges of the regular subdivisions induced by this function. On its support are parallel to I plus or minus, which is the same as saying that every cell in the subdivision is the polytope of an even delta matrix.
You want then in this definition J not equal to I of evaluate record?
Oh boy. Evaluated even. I mean, I certainly want to do even.
Yeah, we said
Matroid.
before.
Probably, yeah. Ooh. Probably. Believe it would be the one to really, okay. Yeah, good. Okay. And as we explored before, sort of natural representations of this are if we take a matrix, an n by n matrix over a field with evaluation that's skew symmetric, then we can take the function to be the valuation of the principal minor, or if we're willing to scale by 1/2, the valuation of the Fathian. What's 2 times the, like, the Bathian S minus matrix. And so Felipe showed that you could, like all evaluated even delta matroids up to like n equals 5 were representable in this way, and after that, because I don't know about n equals 6, but then you go further on than that, then they stop all being representable in this way. Okay. And so the question that we went into this with was like, okay, what is the natural, what is a possible generalization for general, what would it mean to have a evaluated delta matroid? And in particular, one of my personal motivations for doing this is with my student Abir, who's right there and can tell you all about it. So we studied polynomial relations on the principal minors of symmetric and Hermitian matrices. There's some hope that understanding those relations, as with the Plucher relations or the Wick relations, might give some natural tropical relations that we could use and study for the evaluated version. It didn't quite pan out, but I'll tell you, don't be tried. And so in general, so for evaluated delta matroids, the definition we decided to explore was really the one given by regular subdivisions. So for us, we're interested in functions on the cube. Such that the regular subdivision, all edges of the regular subdivision induced by this function on its support are parallel to EI or EI plus or minus E. Those are polytopes of delta matrix. We wanted to see what would happen if we explore this as a definition. So I'll tell you some of the things that we found.
You're still taking the subdivision of the support.
Sorry?
You're still taking like a subdivision of
Of the support.
Support.
Yeah. So if something's infinity, it
Okay.
is. In particular, the support itself is only allowed to have these edges, and so it has to be a delta matrix. It's not too hard to convince yourself that for n equals 2, have any function you like on the vertices of the 0, 1 square, and it's fine. So the first, so things start to get at least a little bit interesting when you consider the 3 cube. And in particular, here is an example of evaluated delta matroid. We could, for example, take the evaluation 0 for even subsets, and valuation 1 for odd subsets. We get a very similar picture as 4. So this is the empty set, 3. So now we have a big, the other tetrahedron. It's trouble. So sitting at height 0 is a tetrahedron in the middle. At height 0, and then all of the corners get lifted up to height 1, and so we break off these other tetrahedra, right? So this is the subdivision that we get. That makes sense. And one of the first things to notice about this is actually a triangulation. So if you think about the height functions that will induce the height functions that will induce this as a triangulation, it's full dimensional in the 8-dimensional vector space of height functions. So that immediately says that this set of evaluated, if this is our definition for evaluated delta matroid, then it's going to have some full dimensional cone for n equals 3, which is already to me a little bit weird. So I'm going to use the notation delta to be the evaluated delta matroids. And so this means that this set is going to be some rational polyhedral fan. This means that it has a cone of full dimension, 8 in this case, which is already a little weird. Which I found at least a little weird. And in fact, if you actually go through and try and write down a characterization for what these things look like for n equals 3, you get the following relation. You have some function. Let's keep it as R. So this is evaluated delta matroid. If and only if the following sort of almost tropical relation holds, take the minimum of the following things. Some of them will look.
Yeah, so 8 is weird because should I be comparing it to 6?
To me, this was strange because it has a full dimensional cone. It's maybe not too hard to convince yourself that it also has some maximal lower dimensional cones. If you don't think it's weird, that's fine. Just, just to note, it has a full dimensional cone.
So it's not even dimensional.
It's not, equidimensional. So if you think about, so these subdivisions that came up in Josephine's talk, where maybe you cut off the split off the empty set and 1, 2, 3, and then try and subdivide this octahedron in the middle. The only way to subdivide it is with this in a delta matroidal way is to really subdivide along a square right down the middle. You can't refine it any further. So that's going to be some other maximal cone, but it's going to have codimension 1.
But realizable ones are 6-dimensional.
I said nothing about realizable ones. Yeah, I will tell you some of the realizable stuff. But I guess so far in the story, we've been looking for tropical relations, right? Been looking for things like the 3-term tropical Pluger relations or the 4-term Wick relations, where the minimum of something is achieved twice. And here, it's not like all functions on the cube satisfy this condition, but there is like a full dimensional cone of them that do. I personally found that weird, but you don't. You can have your own. Yeah, you're welcome to not. And the one way to write down the condition is that if you look at the min of the following 6 things, the first are very closely related to the 4-term Wick relations. 1, 2. And then there's 2 more. 1/2 the sum at all of the even subsets. And then 1/2 the sum at all of the odd subsets. But this minimum is either attained twice or attained uniquely at one of the last 2 terms. That's going to be the statement of the theorem. Twice. Or uniquely at the last 2 terms. At one of the last 2 terms. So in the case of this, where we break up the octahedron, the minimum is going to be attained twice among these top 4. And in the case where we have this blue octahedron, the minimum is going to be attained uniquely at this sum over the even ones. It's not like a tropical equation anymore. So it's, you can think of this as maybe a tropical inequality, but that's the condition for n equals 3. We're going to go up. So just, you go up until you understand something. At some point, we hope that this will be able to stop, right? For n equals 4, it turns out that you do, the codimension is 1. You do get sort of 1 tropical equation. So we have a function. Sorry, what am I doing? So on the subsets of 1 through 4, this belongs. This is a valuated delta matroid, if and only if. I mean, one condition is that if you restrict to any 3-dimensional face of the cube, you get an evaluated delta matroid on 3 elements. So the restriction to a 3-face belongs to it is evaluated delta matroid on 3 elements, and the other is basically what you get if you try to protect yourself against having long edges between antipodal elements of the cube of the 4 cube, which is that some minimum, which I'm not going to write down explicitly, some C's, like a circuit, is attained twice. Where here, so LC runs over like all expressions of sort of the point at the center of the cube, all 1/2, as a convex combination of the vertices of minimal support. Lambda s, ES, and lambda s, non-negative, coming to 1, of minimal support. Of which there are many. I can give, yeah, if people want more detail, I'm happy to give it. But maybe the takeaway is that there's like one big tropical equation, the minimum of a bunch of things that are linear in the values of this valuation. This big minimum is attained twice. That and this condition on the three faces is sort of enough to guarantee that you have a evaluated delta matroid on 4.
Kind of
Yeah.
means everything
Oh.
is an if and only if, or
This is a, yeah, this is an if, I guess you can't see, but this is an if. Yeah. In particular, this suggests that it has codimension 1 in head dimension 15 out of 16 possible, and you can show that it actually does. You can cook up an example. So I'll say a corollary, even though you need a little bit more work, is that the dimension of this is
Multiple LCs.
sorry?
You have multiple LCs, but they somehow all agree in some.
Yeah,
colors.
maybe let me do an example. I should do a small example of what I mean. I mean, so what's one way of thinking of this 3-term Fluker relation? One way, I just erased the octahedron. Surely there's still one on the board. No. One way of thinking of the 3-term Fluker relation is you don't want any edges between antipodal points. And so one thing you can do is you can think about what happens to this point right in the middle. And it lies on the line segment between these two and these two and these two, right? And so what you want is that when you look at where that point would be lifted, were it to take the value coming from like these two vertices, that minimum can't be attained uniquely because you don't want this long edge. So sort of to protect yourself, you need that minimum to be attained twice. So that the value that gets lifted to, or sorry, we're doing lower hull, like it's dropped to in the lower hull, sort of comes from what it would be coming from this convex combination and also this convex combination. So that you get this whole like square that protects you from having a long edge. And so this is attempting to do something similar, except it's worse because there's just more. So what do I mean? So for example, so one such circuit is 1, 2, 3, 4, and 1, 2, 3, 4. And you can write the all 1's half, right? As, let's help you get this right, 1/6 times E1 plus E2 plus E3 plus E4 plus 1/3 times E1 through 4. Hopefully this is a convex combination of these points. And so then the corresponding, so one term is going to be a minimum of a bunch of stuff. There's going to be one term corresponding to this. And it's going to be, so I guess we keep the coefficients. So this will give 1/6 times the value at each of these. Plus 1/3 times the value of that 1, 2, 3. And that's going to be one of the terms that shows up in this big long minimum. And for different sort of minimal ways of writing this as a convex combination of the vertices, you'll get different expressions that sum up in this really long sum. There might, so I should say, this might not be like the minimal thing. We know that this equation works. it might be that you can drop some of these terms and it would still work, and we don't know. Yeah,
Should I think of this as saying that every long edge in the n equals 4 case goes through the middle of the cube?
this is saying every long edge. I mean, this is really just saying that the long edges between antipodal points of the cube cannot show up in the lower hull. There has to be some belt that protects against it. Yeah.
So just connecting the example, so is the sum of lambdas 1 or 1/2?
1.
The sum of lambda.
Let's see, so 4 times 6.
Okay, sorry, yes, I
Is-
missed that the 4, yeah, it's fine.
So hopefully it's okay. 4 times 1/6 is 2/3 plus 1/3. Yeah, so this is really, we're writing this point as a convex combination of the vertices. Yeah, okay. I mean, this is, you know, if you ask your resident polyhedral geometer, who may or not be Gaku Liu, how to protect against long edges, this is the answer that you will get. So this is how one protects against such thing. Okay. I'll talk about representability a little bit, because that's how we got into this. So maybe I'll just say that the good news is that for n greater than 4, so you have a function on the n cube. This is a evaluated delta matroid. If and only if the support is a delta matroid. And the restriction to every 4th face of the cube. Of the cube. Is also is evaluated delta matroid on the corresponding 4 elements. Yeah.
Is it on purpose that here you allow infinity as a value, whereas before you didn't?
I think actually these equivalent, I'm just maybe being a little careful with my characterization. I think these other things probably also hold with infinity. But if you take full support, you can erase this because you'll have the full cube as the support. Okay. So maybe in the last 10 minutes, I'll try and talk about the way that I originally thought about trying to represent such things and what happens. So let's talk about representations. We have one notion of representation. So certainly even delta matroids and valuated even delta matroids are usual valuated delta matroids. So one type of representation is the principal minors of skew evaluations of principal minors of skew symmetric matrices. As we saw before, so symmetric matrices also give delta matroids, and so a natural representation one might hope for is taking these values to just be the valuation of principal minors. So where A is, let's say, an n by n matrix that's symmetric over some field with evaluation. And this will give you a evaluated delta matroid. And if one is feeling optimistic and looking at the analogous things for these other fields, one might think, maybe for n equals 3, this will fill up, this will give you all possible, this will fill up this set that we have here. But actually it doesn't. So the principal minors of 3 by 3 matrices, satisfy an equation. Satisfy something called the hyperdeterminantal equation. I'm not going to write down for you, but they do satisfy an equation, and in particular, if you tropicalize them, then they're going to satisfy the analogous tropical equation. And this means that their tropicalization, their image under valuation, has codimension 1. In fact, this is the only, this one polynomial cuts out the image of the principal minor map. You can talk to a peer for more. But in particular, we immediately see that we're not going to get all valuated delta matroids, even for n equals 3. And if you actually look at the tropicalization of the hyperdeterminant, you're never going to get a subdivision like this top one. So you're going to miss out this whole full dimensional cone. And you look at that.
Am I just categorically add symmetric matrices 6 dimensional?
Codimension, well, okay. Codimension 2. So if you, because of this empty set, yeah, okay, sorry, I'm lying. They're really codimension 2. If you add in scaling, or you treat it projectively, then they're codimension 1. So really plus global scaling.
I should think of it as in space.
Yeah, either you can do that, or you can say, I'm interested in things that look like this. Where lambda is a scalar that's the same for all of them. Yeah, no, thank you. They're indeed. It's and then it's the correct dimension. If you add in the scalar, then you have symmetric matrices are 6-dimensional. Scalar is another dimensional, so you get a 7. It fills up a 7-dimensional thing in the 8-dimensional space. Yeah, good. Okay. So one type of
Are there delta matrices that are representable by skew symmetric matrices, but not by symmetric matrices?
Yes. So I think, yeah, I think it's just the blue tetrahedron. I want to say yes, but maybe I don't want to say yes live. Yeah, so that also, you know, there's something missing. So the thing that that I find tempting is actually using Hermitian matrices over a field. One reason this should be tempting is a theorem of Peter Brendan that Mario, I think, gave some version of, and I'll give a different version, is that if you have a polynomial in, let's say, n variables, that's multi-affine. So all of the monomials that show up are square free. And maybe this is a polynomial with coefficients in the complex Poisson series. And you could also do real Poisson series, but I'm not going to restrict to non-negative coefficients. If this is stable, meaning it has no zeros, all of whose imaginary parts are strictly positive, then if we take the function that records the valuation of the corresponding coefficient, I did not write down the theorem in this way, but this is a valuated delta matrix. This is an delta. Yeah.
This is what he calls in convex, or Murata calls in convex.
Well, as far as I could tell, both he and Murata have tried really hard not to say M convex when you don't have the symmetric exchange property. So this is misquoting the theorem, but there's various versions of this theorem, but I mean, it really, yeah.
I mean, he didn't use the Matroid, this polytope
Yeah.
description.
No, I mean, I'm happy for people to show me references otherwise, but like, as far as I could tell, that people try really hard in the literature to avoid terminology for functions that do this.
Yeah, okay, but I mean.
For even delta matroids, I think they're willing
okay,
to say
but
like M
there was
convex.
some,
Yeah.
like something which was not the polytope formulation, but some inequality stuff, which was reminiscent a bit of M convexity, right? And you
Yeah.
translated this to.
I mean, so the versions that I found, are like, so Brendan has a theorem where he says that the support of this is a delta matroid. That's acceptable to say, and that for things with this strong exchange axiom, then it's a valuated version of that thing, like a valuated even.
Okay, so you even.
But like.
More,
So this is a strengthening of, but it's really, if you go through the proof that the support is a delta matroid, which is really just sort of, if you care about edges, you really just deform to what's called an initial form, which is like an edge of the Newton polytope, and show that that initial form has to be stable, and then ask yourself what binomials are stable. And this comes up. This was also, so Felipe and I and Josephine also looked at this in a paper on positive, like did this out more carefully, more explicitly in a paper on positive hyperbolic varieties. But for this version, like the ideas are all of the technology is there. And people are not willing to talk about such functions. That's what we do. We're just, yeah. Okay, but so immediate corollary of this is that for any Hermitian matrix, for a Hermitian over the complex Bestow space, this is stable. And as we saw in Josephine's talk, the coefficients are exactly the principal meters of this matrix. And so a corollary of that is that if we take a Hermitian matrix, then the evaluation of the principal minors give you evaluated delta. And so maybe just, I'm running out of time. In particular, if you take a matrix like this, leave you to check what evaluated already. So we get this is nice and symmetric. 2 by 2 minors, minus 1 squared. The determinant is minus 3t plus t cubed. And so the valuations you get are 0, 1, 0. 1, 2, 3, 1. And so in particular, you get exactly this valuated delta matroid that lives in the big cell. And more generally, so for n equals 3, every valuated delta matroid is representable by principal minors of a Hermitian matrix. Every what's it doing? What is, let's say, Hermitian representable. And maybe I'll just, I'm out of time, so maybe I'll just mention, you can, if you're willing to work with other fields with an automorphic involution that respects your valuation, you can define sort of Hermitian matrices in that context, and you'll still get valuated delta matroids from taking valuations of their principal minors. The bad news is that even for n equals 4, the image of this is still going to be codimension 2, and so you still don't fill up the Dressian on 4 elements using Hermitian matrices this way. And also, if you're willing to play with field extensions, so in the paper on sign permutahedron and delta matroids by Chris or Alex Fink, Grant Larson, and Hunter Spink, so they look at representations using the maximal orthogonal Grassmannian. You can phrase some of those representations as sort of minors of Hermitian matrices as well. So that also sort of falls into this category. And I'm happy to tell you more about that offline. So maybe I will stop there. Thanks for your time.
Do we have more questions?
So for matroids, there's this construction where you take the hypersimplest and lift it up, and then your favorite, like the rank.
Yeah.
And then, is there an analog with
We
that?
checked, so we learned about the rank from the notes that you had online, and the rank is a evaluated delta matroid. That's
great.
the good news.
I wanted to know that.
Yeah, okay. Okay. In this definition of value.
If I understood correctly what you said in that n equals 3 case.
Yeah.
Couldn't you just list each of those last terms twice and then phrase it as a tropical condition?
I guess so. I guess so. Yeah, that seems also, I don't know if I find that weirder or not than the original thing, but.
I feel like, I mean, that's sort of natural from this algebraic point of view that we, so I don't find that as weird.
Okay. Everyone can pick their poison. Yeah.
So it couldn't be attained twice, like on one of the top ones and one of the bottom. That wouldn't happen.
That's fine. If the minimum is attained here, then you're already sort of
Then
safe.
it's unique.
Yeah. No, if the minimum is attained here, it's allowed to be attained twice among anything. As soon as the minimum is attained at one of these 2 bottom ones, you're like free from having bad edges. Then like this simplex is gonna sort of show up, this blue simplex.
Can it be attained at one of the bottom ones and one of the top ones?
Yes,
Yes, but then doubling the bottom would make it attained 3 times. And
at least twice. Yeah, if I, yeah, that's right. And at least twice. Yeah, good. I mean, you know, and maybe from this morning's talk, the natural question that presumably you also don't know how to answer, if this is like the projection of the evaluated version of the anti-symmetric matroids that we saw, right? I mean, we don't know if all delta matroids come as projections of anti-symmetric matrices. So presumably we don't know if all valuated delta matroids come as projections of valuated anti-symmetric matrices, but that would be like a natural question to ask.
Is there some fundamental representation that has a weight multiplicity true? In relation to Pierce's question of doubling something that's relevant to this.
This is might have said this, but for n greater than 4, do you have defining equations?
Well, I mean, it's so. You mean without the support condition? If you so if you ignore the support condition, maybe you restrict to only having full support, then it's going to be so for every 4-dimensional face of this n cube, you're going to get one relationship like this. For every 3-dimensional face, you're going to get one of these. And that will be, so this theorem says that that's enough. Because what this says is you restrict to every 4-dimensional, so like, is it's enough to look at the restrictions on every 4-dimensional face. So you pick.
Okay, yeah.
So then you'll get, so these will give you the correct relations. Yeah. But that, you know.
Is there any relation between this hyperdeterminant and that theorem n equals 3?
Yeah, so, yeah, this is closely related to the Newton polytope of the hyperdeterminant. But it's not just the straight up, this means it's not up the straight up like tropicalization of the hyperdeterminant. This is closer to what you get if you ask for the hyperdeterminant to be like non-negative.
Should we have known that? Should I have known that the hyperdeterminant was the answer? What, with some collapsing symmetric matrices?
Should you have known? No. I mean, I was starting from, you know, caring about principal minors. And I was hoping for the hyperdeterminant because I knew the hyperdeterminant showed up in the relations on principal minors of symmetric matrices. It also shows up as inequalities for principal minors for Hermitian matrices. So I was like gunning for the hyperdeterminant to play a role somehow. But that's, if you start with principal minors, then it's reasonable to hope that the hyperdeterminant will show up. Just like it would be reasonable to hope that like the Wick relations show up for Appians, or that the Pluker relations show up for the Grassmann. So in that sense, it's sort of reasonable to hope for. Yeah.
Are there any, I don't know, are there any nice subfans for which realizability is more transparent, like it is for the positive direction?
Well, so Josephine on Tuesday gave a talk about principal minors of positive definite Hermitian matrices. And there was sort of a characterization in terms of like slices being realizable over like R or C. So in that, I don't know if you count that as like easy. But yeah, that's
just wanted a few of the, okay.
Yeah. I don't know about like I don't know if there's an even more positive story. It's reasonable to ask for.
More questions? If not, let's thanks.